Hi everyone, happy Tuesday. I hope everyone is doing great today. In yesterday's session, we learned how signals are transmitted through the air. We talked about how RF waves are generated, propagated, and detected at the other end using Heinrich Hertz experiment. To summarize, when we charge any material, such as metal, it accumulates charge due to the movement of electrons. But what is an electron? If you take any material, its smallest component is an atom. Okay, and an atom consists of protons in the nucleus. Okay, and electrons revolve around this nucleus, right? So these electrons get charged when an external source like a battery is applied. When they gain charge, they tend to move from negative to positive and positive to negative with a pause in between. So this movement results in a sine wave, that is nothing but a radiation it creates. While a sine wave is an ideal representation in the real world scenario, the radiation emitted differs slightly from a perfect sine wave. It will not be exactly like this, but somewhat like this. Okay, not exactly the sine wave that is shown here. Today we will expand our knowledge by learning more about the RF waves, the characteristics, the behavior. So all those things we will learn in today's session. I hope yesterday's session was knowledgeable and you were able to catch the concept. So basically in this experiment, you can see a battery is applied, which is nothing but a potential difference or a voltage. You're applying a voltage. When you apply a voltage, so it is going to pass the current, right? Or the electrons. And then that is going to create some radiation, that is going to generate some radiation. So if you take any material, so that is having atoms, any material you take that is made of atoms, that's the smallest component, right, of any material you take. So when you charge, so the electrons try to escape. So they go from negative to positive and positive to negative. Okay, so that generates a kind of a sine wave, and this is not exactly the sine wave, but close to a sine wave. So that radiation is sent in the medium, so that is air. And on the other side, in this experiment, you can see there is a spark generated here. So if you put a bulb on this, so it will glow. Okay, this is a experiment carried by Henry Hertz, where it's a generation of the radiation, propagation, and detection. So this was the stepping stone for this RF waves, you can say, I mean the wireless communication and all. So this was the stepping stone for this experiment. Okay, and also Maxwell has had already come up with the analogy of the electrical waves and the magnetic waves and all. So we'll expand our knowledge a bit more on these concepts today. Like we will understand what are the characteristics of a wave. Okay, if you take a wave is nothing but a radiation. Okay, in a electromagnetic spectrums there are different waves, but our interest is on the radio frequency wave, RF waves. Okay, radio frequency waves, which is used to send the communication. Okay, wireless communication is sent on the RF waves. So ones and zeros are being sent, this information is being sent through these RF waves. To understand this, we need to know how these waves work, what are the characteristics of these RF waves, or any wave for that matter in the electromagnetic spectrum. So if you take a wave, it has got amplitude, it has got frequency, and it has got phase. So we'll understand one by one. So amplitude is height of the wave. Okay, height of the wave. So this is called the crust. Okay, this positive increase. The negative increase, this is nothing but the electrons are moving from negative to positive, positive to negative, right? So that action is going to generate some radiation, and this part of it is called as what? This is the crust. Let's say it is A. The downward part of it, it is called as trough. This is A. So that is A plus A is nothing but 2A. So this 2A is the height of a wave. That height is called as amplitude. Okay, this height is called as amplitude. And this height is the strength of the wave. When I am saying the wave strength is low or wave strength is high, so that means the height of the wave. When a wave is traverse from a brick wall or else a concrete wall, so if it is like this, then when it is passing, okay, after passing it should be, okay. After passing the wall, the height of the wave decreases. Okay, that means what? The strength of the wave decreases when it encounters an obstacle. The obstacle is a concrete wall here. Okay, so that concrete wall decreases the strength of the signal. When I say the strength of the signal decreases, it is nothing but the amplitude of the wave decreases. Okay, I hope this is clear to you. Let me remove this. Yeah. So next is frequency. So frequency is cycles per second. So for 1 second, so how many cycles? It will start from here, one crust, one trough in 1 second. So it is 1 cycle per second. 1 cycle per second. So that is frequency. And frequency is measured in hertz. The unit of frequency is hertz. Obviously named after Henry Hertz. So here in this case, it takes 1 cycle in 1 second. So 1 cycle per second. So that is nothing but 1 hertz. Suppose if it is taking 2 cycles per second, so that is 2 hertz. So 10 cycles per second, 10 hertz. So that is how it is calculated. When we say the frequency is high, that means the cycles per second is more. Suppose this is 1 second and you can see how many cycles are there. So this is 1 cycle, 2 cycle, then 3, 4, 5, 6. So there are 6 cycles per second. Whereas for 1 second, this is like 1 cycle, 2 cycle, 3 cycle. So this is 6 cycles per second. This is 3 cycles per second. So the frequency here is more, whereas frequency here is less. So this is what high frequency and low frequency means. This is also one of the characteristics of a wave. I hope you got this concept pretty straightforward. What is the amplitude? What is a frequency? Amplitude is a maximum displacement of the waveform from its mean or equilibrium position. Amplitude is the height, force or power of the wave. So when we say the signal strength is less, so now we know that the height of the wave decreases. Okay, it is the strength of the signal decreases means the amplitude decreases. Okay, suppose if you want to increase the signal strength, so what will be your answer? How you will do that? You will increase the amplitude of the signal. Okay, frequency is number of cycles per second and the unit of measurement is hertz. It defines number of waves that are generated over 1 second per period of time. Yes, the amplitude is both the upper wave and the lower one here. Okay. The amplitude is the one crest, one trough. So that is amplitude, height of the wave. Then there is one more concept, that is a wavelength. Okay. Wavelength is simply the distance between successive crest or trough of a wave. Wavelength is inversely proportional to frequency. Okay. If the frequency is high, the wavelength is small. What that means? So frequency is high. So in this case, this frequency is high. The wavelength is the top of the two crust or the two trough. Okay, the distance between the two trough or the two crust. So that is wavelength. Okay, the distance between the two crust or the two trough is the wavelength. And you can see here, the wavelength is small here. Suppose say 1. But if you see here, the wavelength is little bit larger here. Maybe it is 2 lambda. So when you, this is what? Low frequency. Low frequency, the wavelength is high. Lower wavelength, frequency is high. So this is inversely proportional. If you increase the frequency, wavelength will be shorter. If you if you decrease the frequency, the wavelength is longer. Okay, so that's the characteristics of a wave. So why we need to know this? Because obviously we are sending the data on the air through this radiation, and we should know how this radiation works, right? So these are the characteristics of a wave, where amplitude, wavelength, frequency, and phase, these are the characteristics of the wave. Now we know that if I want to have a good signal strength, I will say the amplitude should be high. When the amplitude is high, the signal strength is high. When a wave hitting a concrete wall, then its strength decreases. That means what? The amplitude of the signal decreases, and and also there are other factors like any attenuation, free space path loss, which we will be learning. So over a period of time, when the wave is traveling, so it will lose its strength to lower degrees. Okay, to like say minus 120 dBm. Okay, so eventually the signal will fade away. Okay, on its own, if it is not coming across any obstacle, but still because of the free space path loss, it will eventually degrade or fade away. Just remember a person sticking his hand in the pond, right? It generates the ripples, and the ripples, as they move away from the finger, so it gets weaker and weaker and it will fade away. Similar concept with the waves as well. Okay, at the epicenter of the impact or at the antenna, the amplitude is high. But as they go away from the antenna, the amplitude is less. The amplitude will fade away slowly. Okay, so that's the concept. And the next concept is phase, which is a very important concept. Phase is the relationship between two or more signals that share the same frequency. Phase is nothing but it is in relative to the two waves. It is not, we are talking about the single wave, but the two waves we are comparing. So one wave, suppose this is the main signal, this is the ideal signal, and you are sending one signal and it matches the ideal signal. So then it is in phase. If the wave is like 90 degrees out of phase, so this is 90 degrees out of phase. So for example, you're starting a wave like this. Okay, this is your main wave. And now one more wave just starts like this. Okay, this is 90 degree out of phase. It is 90 degree out of phase. Why it happens like this? Because this started at a period of time, maybe 1 This started at a period of time, maybe 2, but they have the same frequency. Just remember, they have the same frequency, but the phase is different. Why the phase is different? Because the frequency is same. The frequency on which they are traveling is same, but they started at a different time. So then what happens? They will be in a different phase. There are three phases like 90 degree, 180 degree, sorry, four phases, 90 degree, 180 degree, 270 and 360. So this is 90 degree out of phase. So compared to this ideal signal, so this is like 90 degree out of phase. And if a signal starting like this, then it is 180 degree out of phase. So what I'm trying to tell is, if you have a signal like this, okay, so the another signal starting from here, 90 degree, okay, one more signal starting like this, exactly opposite, that is 180 degree out of phase. If it is 270, it will start from here like this. So they have the same frequency, means what? The wavelength is same between the crust, right? But they start at a different time. They start at a different time. So since they start at a different time and have the same frequency, they tend to increase the signal strength or decrease the signal strength. That means what? The amplitude will decrease. When the signal is traveling, in outer space, it is not a bounded medium, right? Whereas Ethernet is a bounded medium where you don't find any obstacles unless they are, passing some device, right? If it is a plain cable, so there is no obstacle. But while you are sending the signals on the wireless, so these have lot of obstacles in the nature, and also on the it can be any physical material, it can be a natural phenomena. When the sun is shining on a metal, so that creates a radiation, and that radiation has the same frequency as the one that you are sending through your antenna. So through your antenna you are sending a signal at maybe 2.4 gigahertz, right? And not exactly 2.4 gigahertz, maybe 2.5, or some particular frequency. A sun shining on a metal, it generates some radiation. It is also having close to the same frequency. The wave is on the same frequency. So since they are on the same frequency, but they are out of phase to each other, they tend to cancel or add to the signal. So that means what? Suppose they are out of phase, and if it is exactly 180 degree, they will cancel each other. Suppose if they are like in phase, so then they will add the signal. If two signals collide, when they collide, if the amplitude is same? No. If the frequency is same? Yes. Okay. When two signals collide and they have the same frequency, then they tend to add up, or then they tend to cancel each other when they collide. When two waves collide and they have the same frequency, they collide. When they collide, they will gain the amplitude or they will cancel the amplitude. Okay, so that's the concept. So phase is nothing but it is the relationship between the two waves. If you have a wave that is like this in our case, and one more wave which is exactly in phase, that means it is starting at the same time and it is having the same frequency, then they tend to add to each other. If it is 180 degree out of phase, then they will cancel each other. Okay, so that's the concept of phase. Phase can be measured in distance, time, or degrees. If the peaks of two signals with the same frequency are in exact alignment at the same time, they are said to be in phase. Conversely, if they are not in exact alignment at the same time, they are said to be out of phase. Okay. The phase involves the relationship between the position of the amplitude, crust, and troughs of the two waveforms. I hope you got this concept, okay, of what is amplitude, wavelength, frequency, and phase. As we go through this course, you will understand what is the significance of these characteristics. So quick notes, Electromagnetic waves oscillates perpendicular to the direction of the wave propagation. They consist of oscillating. So this we know that electromagnetic waves exist across a broad spectrum of frequencies. Okay, electromagnetic waves, it has a broad spectrum of frequency that we'll see in the next slides, coming slides. Frequencies, wavelength ranging from low frequency radio waves with a long wavelength of high frequency gamma rays. Okay, this we'll discuss in the next coming slides. In a vacuum, all electromagnetic waves travel at the speed of light. Electromagnetic waves are described by Maxwell's equation. So electromagnetic waves can travel in a medium or without a medium as well. Okay. It describes how electric and magnetic fields interact and propagate through space. We increase amplitude of a wave, the strength of the wave increases. Thus, it can travel long distance. The energy carried by an electromagnetic wave is proportional to its frequency. Higher frequency waves like gamma rays and X-rays carry more energy. Okay, gamma rays and X-rays. So these are lower frequency waves. It's not a good diagram to represent. So higher frequency waves are like gamma rays and X-rays. So they have more energy per photon compared to the lower frequency waves, that is the radio waves. So these radio waves, right, FM waves and all. So it will be, the amplitude will be like a height of a building. Okay, height of a building. Okay, so it will be like height of a building. So that much bigger waves it will be. Okay, radio waves. So gamma rays, X-rays have lower frequency, whereas the radio waves have the higher frequency. The amplitude also high for these radio waves. I hope you got this concept. So then there is one experiment called as double slit experiment to understand the wave particle duality of these waves. Whenever we are talking of RF waves, so it is similar to the it is similar to our light waves. Okay, so in this there is an experiment called double slit experiment. This is to understand how the waves behave. Okay, the waves, the RF waves can be have a particle wave particle duality. So wave can be like this. The particles will be like this. So in this experiment, as you can see, there are some screens here. There is a gap in this screen, and here also there is one screen. So sorry, this is some material. Okay, and this is a screen. So when you emit some radiation here, so see how it is going like this, and it will parse this material and go to this, and on the screen it will display here. I mean, it will be showing some pattern. But if it is a particle, right? So if it is a particle, so then it will pass this small gap, and it will go here. When it pass and go through this gap, and it is on the screen, so it will look like this. That is over here. If it is a wave, so then it will look like this. So that is what this experiment is in a nutshell. So this is very complex thing, but I am explaining you on a high level. We, as a wireless engineer, no need to go much deeper into the calculations and all. Just we need to understand the analogy overview, how it works, because we just need to understand how these waves work at the end of the day. So when a radiation is emitted, just like we saw in Henry Church's experiment, the radiation is emitted. So if it is emitted, if it is a wave, to prove that, this is the experiment. So if it is a wave, so it will pass this material. Suppose it can be made of plastic, it can be made of some metal. So what happens is, it will pass, the waves will pass this object, and it will shine here like this on the screen. If it is a particle, so then it will pass through this pass through this gap, and it will not pass these walls, right? Because it's a particle, it cannot pass the walls. If it is a wave, then it will pass this metal or plastic, whatever is in between, right? That's the characteristic of a wave that we are learning. If it is a wave, obviously it is going to penetrate, right? If it is a particle, it will not penetrate, it will find for these gaps, and from there it will go. So that's a particle. If it is a wave, it will penetrate. So that's what this experiment is explaining here. Okay. And yeah. Now let's just understand the electromagnetic spectrum. So there's a question, if it's 90-degree out of phase, so it will not cancel 100%, right? It will cancel some part. Yes, that is correct. It will cancel some part. Okay, let's move on to the RF electromagnetic spectrum. So electromagnetic spectrum, it is nothing but it ranges from the low frequency waves to the high frequency waves. Okay, the electromagnetic spectrum. So at the higher frequency, sorry, the lower frequency, you have the radio. Here you can see the penetrates Earth atmosphere. So the waves should escape the Earth atmosphere, right? So what are those kind of waves which can penetrate the Earth's atmosphere? So radio waves, you can see yes, microwaves, no. Then infrared. So here you can see these are no, big no. So radiation type wavelength, this is the wavelength 10 to the power of 3, okay, 3 times, right? Radio waves 3 times if you do, so that's the wavelength of this radio waves. And the frequency is 10 to the power of 4, and it is in hertz. So 10 to the power of 4 means how much? 4 times 0, right? So 10,000 cycles per second. Uh, the frequency, okay? This is 10 to the power of 8, 10 to the power of 12, 15, 16. Just imagine how many cycles per second. These radio waves, microwaves, infrared, and visible. So radio waves have the lower frequency. That means this thing. When I say lower frequency, you need to understand that the cycles per second is less. It is less compared to this, but 10 to the power of 4 means obviously it is high, right? 10 multiplied by 4 times. So those many cycles per second. Microwaves 10 to the power of 8 frequency. Then you have infrared, visible, ultraviolet, X-ray, and gamma rays. Okay. And radio waves, as you know, it is used for TV, mobile, Bluetooth, radar, RFID, and all. And these radio waves start from 3 hertz to 300 gigahertz. And microwave starts from 300 megahertz to 300 gigahertz. All right. So as you can see, this is overlapping, right? So microwaves are the subset of the radio waves. Radio waves, okay? So this is the frequency range of the radio waves and the microwave. Radio wave start from 3 hertz and ends at 300 gigahertz. Microwave starts from 300 megahertz to 300 gigahertz. All right. And this is falling inside that, like radio waves comes, microwaves comes inside the radio waves. And the one that we are using for Wi-Fi, there are 2 bands, okay, 2 spectrums. What is a spectrum? Like this is radio waves, right? So it has a range of frequency. It starts from 3 hertz, 3.1, 3.2. Then it goes all the way till 300 gigahertz. So those many frequencies you have in this radio waves. So this is a spectrum, the collection of frequencies that is called as a spectrum or as a band. Okay, we will learn more in detail in the channels section. But spectrum or a band is a collection of frequencies. So radio frequency spectrum, RF spectrum, it is having a range of frequency. In that range of frequency only microwaves will come. Okay, in that only our Wi-Fi band also falls inside this radio waves or the microwaves. So Wi-Fi, like we use popularly 2 bands, that is 2.4 gigahertz and 5 gigahertz. Okay, these are the 2 bands that we will use. The latest one is 6 gigahertz. Okay, 6 gigahertz. 2.4 gigahertz. That means what? 2.4 billion cycles per second. Okay, cycles per second. So visible light falls in between somewhere here. Okay, and on the other side, you can have infrared, microwave, and radio, and ultraviolet, X-rays, and gamma rays on this side. This is having the higher frequency, and when you have the higher frequency is high, the penetration is less. So gamma rays, X-rays. So X-rays are used in a lab environment, like you go for X-rays, right? So it is within the room. So it is not going to go outside the room. The penetration is less. But if you take radio waves, the penetration is high. When the frequency is high, the penetration is high. Okay, and frequency is less, the penetration is less. Sorry, the frequency is high, the penetration is less. Frequency is low, the penetration is high. Okay, so that is how it is there. So X-rays, because it's having the lower frequency and the penetration is less, so that's why it is used in X-rays. Okay, then you have the gamma rays, ultraviolet rays, visible, then infrared, microwave, and radio waves. And infrared will start from around 300 gigahertz to 400 terahertz. Okay, then visible light is from this, we should know, like 400 terahertz to, I think, 800 terahertz. Okay, 800 terahertz. So this is the visible light. Then ultraviolet is like super frequency, higher frequencies, 800 terahertz to 30. Okay, so this is the range for ultraviolet rays, 800 terahertz to 30 petahertz. Okay, and this is the range. So what is the range for our for the audible sound? If anyone knows, like for the audible sound, it is 20 hertz to 20 kilohertz, right? That is the audible sound frequency. Yeah. If it is a hyper sound that you cannot hear, right? That is 1 gigahertz hyper sound. Okay. So that's the human range that you can hear between 20 hertz to 20 kilohertz frequencies you can hear. So obviously we are sending it on the RF waves, radio waves, that is 3 hertz to 300 gigahertz. Between this we are sending the radiation. But for Wi-Fi signal we are using only 3 bands. 2.4 means, so not only 2.4, there is a range of frequencies which we'll discuss in channels and bands in the coming section. Okay, but just remember that it is 2.4 gigahertz, 5 gigahertz, and 6 gigahertz, and it falls within the microwave. Since microwave is part of the RF spectrum, it's a broader spectrum. In that only microwave comes 300 megahertz to 300 gigahertz, right? So 2.4 gigahertz. So it sits somewhere in the microwave range, right? So that's why when you have the microwaves and you have the Wi-Fi AP and all, you should be a little bit careful. Sometimes when the AP is running and microwave is on, so the signals might collide there. Okay, but it is in the bounded medium it happens, so there are less chances that it can penetrate and go out, but still it can influence your Wi-Fi signals, microwaves. Okay. So in the real-time signal, how we can, yeah, higher frequency, lower penetration, that is true. And how can we assume these ranges in which we are operating? So we don't, so when we have a AP, right, we have a AP and AP has an antenna. So this AP has few modules that will generate these RF signals and it will be sent through the antenna. And we would be sending it on 2.4 or 5 gigahertz or 6 gigahertz radiation we would be sending. So how we would be sending? So that is transmitters work, right? But we can send whatever signals we want. Suppose if I want to send for Wi-Fi, I want to use 3 hertz, right? So I want to use 4 hertz for Wi-Fi. Is anybody going to stop me? No, I can use it for Wi-Fi for 4 hertz. But these are the bands that are allocated by some regulatory bodies like IEEE, ISO and all. Okay, so they have allocated these bands for Wi-Fi usage 2.4, 5 and 6. So there is a board that is called Wi-Fi Alliance that we would be learning in the later section. So that regulates these devices. If you are a part of if you want to produce some device like a AP which is going to send radiation, then you need to get certified from the Wi-Fi Alliance, and they certify this device to be 2.4 gigahertz, 5 gigahertz. Then you need to build the transmitter accordingly, and then it is going to send the signals on that particular band. Okay, so that you don't interfere with other ultraviolet X-rays or gamma rays or any other things. So Wi-Fi has a dedicated band, in that only you can operate, so that the waves don't collide. If they collide, as we know the characteristics of a wave, when two waves with the same frequency in the same space, they meet each other, then they tend to cancel or add the amplitude. When they add the amplitude, signal strength will increase, or when they cancel each other, the signal strength will decrease, or they can cancel completely as well. Okay. So while we go through this course, you will learn so much complexities in this, that we will keep almost the same frequency and we will send, but we will adjust the amplitude and phase and we will send. Okay, we will generate different waves with almost the same frequencies, but we are changing the amplitude and phase little bit there. But we are not doing it. It is the internal mechanism of the AP that does that. We need to know the concept. That's it, like MIMO, OFDMA and all. Okay, so that we will learn in the later stages. So this is just the introductory sections of classes where we are just trying to get a hang of basic wireless stuff. So what are RF waves? RF waves are a type of electromagnetic radiation that fall within the radio wave portion of the electromagnetic spectrum. RF waves have frequency ranging from 3 kilohertz to 300 gigahertz. Okay, RF waves cover a broad range of frequencies, including the AM and FM radio bands. It is used in television broadcasting frequencies and microwave frequencies. RF waves are used in technology like Wi-Fi, Bluetooth, radar systems, MRI, microwave ovens, scientist research. RF waves are used for communication with satellites as well. RF is not sound, not any pressure. It is similar to light waves. Okay, Wi-Fi device sends signals, that is RF signals. RF waves have numerous beneficial applications. Exposure to high level of RF radiation can potentially have health effects, but not too much. Why? Because if you see here, the visible light, so it comes after visible light, infrared, microwave, then the radio waves are there. So visible light is getting emitted on you, right? I mean, you are in the space where visible light is there. So that only is not making any difference to you. Then how come the radio waves, which is less frequency, microwave and infrared, if you expose yourself to that, so it is not going to much difference. So that's why in the food and all we are using microwaves, right? When the food gets heated up in the microwave, so what exactly you are heating there? Not the food. In the food there is a water content, right? So that is what you are going to charge. It is not the food content that you are heating, but the water particle inside that food, that is what you are going to boil, you can say. So yeah, this we will learn in the attenuation. So the reason why I brought this up is, when a wave is traveling, right, so the maximum attenuation will happen when it meets the water bodies. Okay, so you will learn that in the attenuation section. Understanding the carrier signal. So what's a carrier signal? So carrier signal is, there is a normal wave. When the transmitter is there, you have a transmitter and you generate the RF waves. How you are going to generate? It's an internal mechanism of the AP. So it has a module called transmitter, so that it is going to generate the RF waves. When it generates the RF waves, it is going to modulate it with the information of ones and zeros. So that modulated signal is called as carrier signal. Okay, carrier signal. So because data ultimately consists of bits, the transmitter needs a way of sending ones and zeros. So when I say I am sending ones and zeros means I am doing some modulation technique here. Okay, we are doing some modulation techniques like the frequency modulation, amplitude modulation, phase modulation we are doing, and then we are interpreting that particular wave as a one or a zero. So like that we are interpreting. So we are actually not sending ones and zeros, right? So we are sending a wave. So the wave, how it is present. So in what phase is this coming? How much frequency is there? So depending on that, so I can assume it as one or I can assume it as zero. Okay, I can interpret as one or I can interpret as zero. So that's what when I say I'm sending zeros and ones, it is nothing but I'm sending the wave only. But how I am interpreting those waves, so that is what matters. If a signal fluctuates or altered even slightly, the signal can be interpreted wrongly interpreted. Okay, if the slight modification also happens, so suppose if you are sending a signal from point A to point B in air through in the atmosphere, you're sending a signal, right? So there can be a lot of abstraction. There can be a tree in between. Okay, there can be other radiation that is happening because of which this wave can get influenced or modulated, right? The signal will decrease. So there are different ways because of which this degradation will happen that we'll learn in the attenuation section. But now what I'm trying to tell is what's a carrier signal. So carrier signal is a signal that is modulated with data. Okay, that's a carrier signal. Three components of wave that can fluctuate to be modified to create a carrier signal. So you can change the amplitude of a wave, frequency, and a phase of a wave, okay, to send this data. This method of manipulating a signal so that it can represent multiple pieces of data is known as keying method. A keying method is what changes a signal into a carrier signal. It provides the signal with the ability to encode data so that it can communicate. So let's see how it will modulate now. So if I modulate amplitude and I interpret the data, so that is amplitude shift keying. Amplitude shift keying varies the amplitude or height of a signal. So if you see, there are one crust, one crust, trough, and a crust. So this is having one amplitude, maybe say one. This is having another amplitude two. So it is being sent for some amount of time. Okay, period, say 1t. So when the receiver receives a signal for this particular time at this particular amplitude, so that is considered as zero, and this part is considered as one because it is having an amplitude of two and it is sent for maybe time 1t. Then it will interpret as one. So this is amplitude shift keying. Okay. What if another there is a Wi-Fi space? There is one more Wi-Fi space. There is other WLAN that is present in your network, and both are operating on a 2.4 gigahertz band. And then what happens? They collide with each other, and it might influence the amplitude. And this one also, the amplitude will decrease. So then, the misinterpretation can happen, right? So, but what we are learning now, just how the data is modulated. Frequency shift keying varies the frequency of the signal to represent the binary data. The faster frequency wave is interpreted as binary 1 and the slower is represented as 0. So you can see lower frequency, higher frequency. Lower frequency is represented as 0, high frequency as 1. Suppose say this is at 3 hertz. This is at 4, this is maybe 20 hertz. Okay, this is higher frequency, lower frequency. So that is interpreted as 0 and 1. Phase shift keying, you can see here, from here to here, it is in one phase. Again, the phase is getting changed here. Here, once the phase gets changed, So then this data also will change. The interpretation also will change. If the phase continues, just in this case here, so you can see, then again, same thing. So there is no change in phase. If so, what I'm trying to tell is, see, this is, sorry. So if it is going like this, so this is in phase. Suppose the same thing, if it is going like this, again it starts from here. So that means what? This signal is not in phase, so that it will be interpreted as 1. If it is same phase, that will be interpreted as 0. So that's phase shift keying. Okay. So you just change the phase. Changing the phase is nothing but you might be sitting in a chair like this, not exactly. And now instead of sitting and pointing towards the door, you will sit opposite to the door. I mean, in the other direction, like this, here, this side. So that's what phase means. You're changing the phase of the signal. Okay. Wave propagation. RF waves behave similar to light waves. Waves are sent radially from access point. They go in 360-degree pattern. So just one question for you. When I'm sending a signal, we know that we are sending the radiation, right? So we are sending the radiation, but there is a AP. Okay, AP. Maybe we are using a patch antenna. And now one person is sitting here, another person is sitting here, one more person sitting here. So now if I am sending a sine wave out of this AP, am I sending like this? One sine wave to him, another sine wave to him. What do you think? I'll just unmute yourself. Yeah. So what do you think? Like, suppose there is a WLAN. Okay. You have a AP that is here. And now there are 3 clients here. And now the AP has to send some data. How we are sending the data? We are sending it through waves. So now I am sending the data to him like this. Now I am sending the data because like this. So are we going to send the signal in this fashion? Like one sine wave to him, another sine wave to him, another sine wave to him for sending the data? No. So we are not going to send the signal one at a time to everybody like this. Okay. So we are going to send the signal in 360-degree direction. That means what? You have a AP and AP sends the signal like this radially. 360-degree directions you are going to send like this. Okay. So just remember the ripples that gets created in the pond, right? Just remember that example when a person sticks his finger in the pond, so it generates the ripple radially in 360-degree direction, 360-degree. So same way, when the radiation from the AP is going out, so it goes in 360 direction like this, 360-degree direction. So I'm not sure how, okay, like this, like this, like this. Okay, suppose the AP is here, the signal goes radially like this, radially like this, radially like this. One person is sitting here, so he will receive the data. Then how come? Because is it going to send ones and zeros same for him also, ones and zeros for same for him also? Then how the data will be interpreted? So the answer to that is the wireless medium is a half duplex medium. Half duplex. That means what? When one person is getting the data, so the other person is idle. Okay, only one person can listen and receive the data at a time, either the AP or the client, and no other clients will receive the data at the same time. So it's a half duplex medium. Then is it not create a overhead in the WLAN? So there are complex technologies like the MIMO and the OFDM and all, which will help with these kind of issues. Okay. So that we will learn later. But the basic concept is the WLAN is a half duplex medium. And when you send the radiation, it goes all around in a 360-degree direction. Okay. And each person will be heard at a single time, or he will receive the data at a single time. At the second period of time, the other person will receive the data. Each will have their own turns defined. That is nothing but the time division multiplexing. Okay. Each client is going to receive the data on his turn. That is the time division multiplexing. And these time slots will be fair enough. Like he will be served for like time one, he will be served for time two. So like that, the time slots will be decided. So that's what the TDM is. Okay, that we will learn in the modulation techniques. But this is just to give you the idea how these signals are propagated in a medium or in the air. So when the radiation goes out of the antenna, so it goes 360-degree radially, and it is going to serve to a single client. And once that is done, it will send to the next client. So it is like that. So that's what the wave propagation is. Then we have the free space path loss. Free space path loss is, just remember again, the person sticking his hand into a pond, the ripples get generated. And if there is no obstacle also, the ripples will fade away after some amount of time. Suppose if you have AP here, now what happens? You are sending the signal. So this, at this point of time, your signal is maybe 1 dB. So what is a decibel? We will learn in the next session, that is in measurement. So when the signal goes out of the AP, it is 1 dB. Suppose it travels a meter away. So then it will be decreased to maybe say a minus 70 dB. Okay. Then it will go little bit far, maybe 2 meters away. Then it will be like minus 120 dB, and then it will eventually fade away. Then it becomes a noise in the environment. Okay, it will not, you cannot use it. It will be noise. Nobody will able to understand it. But yeah, so that's called noise. So that we will learn later. But what I want to tell you is when the radiation goes out of the AP, it is going to degrade exponentially. Okay, because it is in all 360-degree direction. The radiation is going in 360-degree direction. So the signal strength will decrease exponentially. Okay, and free space path loss is also one factor for attenuation. Signal propagating in a medium tend to lose its strength as it travels away from the transmitter. Signal strength drops exponentially with respect to the distance traveled. We need to make sure signal is strong enough while it gets to the receiver. Okay, so receiver is able to receive the signal at maybe minus 90 dB. Okay, so this is the receiver signal strength indicator, RSSI, receiver signal strength indicator. That is nothing but the RSSI. Okay, so at what dB the receiver can understand the signal. So that is what the RSSI is, receiver signal strength indicator. We need to look at wireless signal received by the receiver and need to make out if the signal is good or bad. For this, we can use receiver signal strength. As the device goes away from the access point, its data rate will go down. If the signal strength is more, we can put more information. If the signal strength drops, right, the data rate will go down. Why and all we will learn in the later stages. But just remember this rule: when the signal strength is high, the data rate is high. When the signal strength is low, the data rate is low. Transmitter. So these are the RF components. We will just cover the RF components and close for today. And tomorrow we'll go for the wireless measurements. Okay. So RF components. You might be curious to know how these signals are generated and propagated in a Wi-Fi space. Obviously, we have a AP. AP in tomorrow's session, if possible, I will just show you the inner picture of the AP, which has different components in it. That is called as a radio chain. Okay, it will have the transmitter, DSP chips, then antenna, all those things. Okay, that forms a radio chain. So data will be sent, suppose from a laptop, right? Data is sent. So it comes to the AP. AP has a transmitter, and transmitter generates the RF waves. And then it is going to send on the cable as a signal. And then it goes to the antenna, and antenna sends this radiations out. And this antenna, when it is sending the signal, so this at this point it is called as EIRP. Okay, what is EIRP? I will just explain in some time. So at this, the beginning of the antenna, that is called as intentional radiator. Okay, intentional radiator, that is nothing but IR. The computer hands off the data to the transmitter, and it is the transmitter's job to begin the RF communication. When the transmitter receives the data, it begins generating an AC signal. We know the inner mechanism, right? So through the through the Hertz experiment and also my analogies that I gave yesterday. So we know how the signal is getting generated through the AC signal. This AC signal is determines the frequency of the transmission. So somebody asked how we know that it has to communicate in that particular frequency. So that is because of the regulations. You have built the device and you say to the device that it has to build a AC signal, and that signal should have some particular frequency. Suppose it is supposed 2.4 gigahertz, it will create a 2.4 gigahertz. And also in that particular channel will be there, so that it will generate. That is nothing but the frequencies we are generating, what frequency it should be. And oscillations determine the frequency of the radio waves. How many oscillations, cycles per second. Intentional radiator, a device that intentionally generates and emits radio frequency energy by rotation, by radiation or induction. It is something that is specifically designed to generate RF, as opposed to something that generates RF as a byproduct of its main function, such as a motor that incidentally generates RF noise. Okay, so you have a motor in somewhere near you, and it incidentally generates RF noise, right? So that's also a RF signal. That's a byproduct of some function. Regulatory bodies such as FCC limit the amount of power that is allowed to be generated by an IR. Suppose if you want to send the signal to the longer distance, so what are you going to increase in an AP? So obviously you're going to increase the power. When you increase the power, the amplitude also increases and the signal strength increases. The distance it can travel is more. Okay. When you want to increase the signal strength in an AP, so what you are going to increase? Amplitude. To increase the amplitude, what you need to do? You need to increase the power in the AP. Okay. The power output of the IR is thus the sum of the components from the transmitter to the antenna, all cables and connectors, and any other equipment. That power level is typically measured in milliwatts. This we will study tomorrow. What is a milliwatt? Okay, or decibels relative to milliwatt. Decibels is nothing but a relative value. Milliwatt is the actual unit of power. Okay, we'll study this tomorrow. So there is something called equivalent isotropically radiated power, EIRP. Okay, EIRP is the highest RF signal strength that is transmitted from a particular antenna. Equivalent isotropically radiated power. So when the signal is transmitting from the transmitter, so there is antenna cable. So the antenna cable will have impedance, that is nothing but resistance. So cable will have some resistance, right? So maybe you generate a signal strength is will not be the same when they travel through the antenna. And also there will be some components like arresters, like lightning arresters, then some multiplexers, or it can be some other devices and all. So if it passes through that, then they will also have some resistance. So the signal strength will decrease there, and it will reach the intentional radiator, and then it is going to go to the antenna. Here it is called as the EIRP at this point of time. So EIRP is nothing but transmitter power and the loss that it got in the cables and the antenna gain. Okay, so there will be some cable loss here. cable loss will be there, but antenna, once you feed it to the antenna, right? Till this point, the signal strength is suppose 10 dB. Okay. When it reaches to the antenna will boost up with 2 dB. So it will become 12 dB signal strength. So the signal strength is measured in dB. Okay. Why and all tomorrow we'll see that, but it will be 12 dB, and the antenna will provide some gain. Okay. How it will provide, and what is active gain, passive gain and all we'll learn in the antenna section. But just to summarize the RF components, so there is a transmitter, there are antenna cable, lightning arresters, or it can be some boosters in between. It will be there, so that will decrease the signal strength. The signal is generated at 10 d, suppose 15 dB. Okay, because of these attenuation that it comes across at the intentional radiator, so it will be less. Okay, then this point, that is before to the antenna, these connectors, cables and all, so this becomes the intentional radiator. Okay, along with the transmitter, these cable and all, this much point is called as the intentional radiator. So equivalent isotropic radiated power is nothing but, so all of these, so whatever 15 dB minus 2 dB of resistance, another 2 dB, and then it will be the 10 dB. Okay, that is EIRP plus the antenna gain. Antenna will provide 2 dB, so it will be 12 dB. While the transmitter generates the signal at 15 dB, at IR it is like 10 dB, but at EIRP it will become 12 dB again. Okay, so that's what the intentional radiator is. It is transmitter plus cables plus other connectors. So all these things forms the intentional radiator. Intentional radiators are the regulated APs or any other device that are that can generate these RF signals. Unlike any natural phenomena where a sun shining on a metal and automatically generate some radiations, right? So this man-made radiations that you create, so there is a body called as FCC who will regulate this. Okay, and are saying that you can provide only this much amount of power outside your device. Okay, so all those things we will see in the measurements, like how much we are allowed to generate the power. So more power you provide, it will go more place. Okay, it will go far away. Will IR do something, decrease the signal or increase the signal? Okay, so IR do something. See, that is just a terminology. IR is nothing but the transmitter plus the cables and the connectors. So till that point, it is called as the IR. Okay, that's just a term. EIRP is also a term, that is all of this. Okay, whatever the plus and minus, all of this plus the antenna gain, that is the EIRP. This is the actual power that is going out, 12 dB. Okay, the generated power is from the transmitter is 15 dB. When it passes through the cables, it will be attenuated, and then this is at the starting of the antenna, that is IR. So this value is called as IR. When it is going out of the antenna, that is EIRP, equivalent isotropic radiated power. So this is the actual power that will go out of the antenna. Okay, that's the terminology. Why IR do something that decreases the signal? Or Shahrukh, that answers your question, I guess. Why higher frequency has lower penetration? Okay. Wavelength is shorter. Yeah, that is one of the answer. Yeah. So that is by design. Okay. So I cannot, the frequency when it is lower, see, when the frequency is lower, the signal strength also will be less. Frequency is less means, sorry, I'm not sure why I'm not able to write. Okay, so the frequency is less, the penetration will be less. Okay, that's the main thing. And yes, wavelength is one of the factors because of which the penetration will be less on the devices. And also, when you have a hard material or a plastic or some screen is there, so depending on the thickness of the material also, the penetration will depend on that. Okay. So that we'll see more in the attenuation section. So we'll talk about it. But today's class was to understand how a RF wave behaves and what are the different electromagnetic waves that are present in electromagnetic spectrum. We know that we are going to use the RF waves to send the Wi-Fi signals. Okay, and what are how you can modulate the signals. It is very basic terms. Okay, we will learn even more complex technologies for modulating the signals. Then we know that how the wave is going to propagate. It is all in a 360 degree direction, just like you are if you blow a balloon, right, it gets expanded. It goes expanded, expanded, expanded. At the end it will try to limit its strength at the end. So that's how this you that analogy you can use. Okay. And also ripples that are created in a pond, that picture you need to remember, that will help you across the course. Free space path loss, we understood. Okay, RSSI, signal strength, receiver signal strength. So what are the components of components in the RF components we have understood. Yeah, so I think that should be good. So tomorrow's session, we will do the measurements. We will understand what is a dB, what is a milliwatt, what is an antenna. So these things we will cover in the tomorrow's session. Okay, we'll expand our knowledge more on antennas and measurements. Yeah, so that's about the tomorrow's session.